Hello! So, in this video we're going to go over the code for rays and their intersections with various shapes. As always, all of the code is available on GitHub, link in the description, and let's get right into it. So the first thing we do in this file is we define these two constants. So what this is doing, it's bounding every ray intersection between a minimum distance from the start point and a maximum distance from the start point. So there are good reasons for both of these. So for the minimum, it's there to prevent any rays that are being emitted by shapes from intersecting with the shape they've just come out of. Because you don't really want it to intersect at the distance of 0, and sometimes due to inaccuracies with floating point values, you might get a very small but non-zero result, even though it should be 0. So we put this limit there. So realistically, nothing is really going to be that close. So it's just a sort of safety check in this one edge case. And the reason we have the maximum value is more for certain special cases. So we've picked a value here that's so large as the default that it's unlikely to ever actually matter. It's very rare that anything will be beyond this distance, but we put it in anyway because we can override this default value for certain rays. And we'll discuss it in more detail later, but shadow rays, which are just to check whether you can see a light directly or not, we don't care about anything behind the light, so in some specific cases we'll want a smaller maximum value, but this default is sort of infinite in a way to disable the maximum value checks that when we don't need them. And so next we define the ray structure itself. So as I explained in the previous video, rays have an origin or a start point and a direction. Now we also store a T-max, so that is by default the maximum default that we just talked about, and by setting this smaller, that's where the override comes in. So now, as usual, we have several constructors. We have default rays, we have copy an existing ray, and also fill in all the details. Now notice this constructor has this last parameter with a default value, which means it's optional. When we want to create rays, we can use this constructor without giving it anything for that third value, and it will just use this default instead. So if we look at the code for these three, they're very simple, very predictable. We just pick some default values for this one. This one we copy the values of the ray we're given, and this one we fill in the values as given to us. So we also define the D constructor for the ray, but we don't need to do anything with that. I've said this before and I'll say it again. I think it's a very good habit to define D constructors everywhere, even if they're not really required. Just because it makes you think about whether it's needed or not. We also defined the equals operator on rays, so this allows us to basically copy other rays into each other after they've been created. It's more for making the syntax look nice than anything. And then the last thing we want to be able to do with our rays is calculate the point with a given t. So what this does is, in the previous episode I explained the ray equation, how we can use the t value in that equation to get any point along the ray. So this function, when it's given a t value, will find the point on the ray that corresponds to that value. So this is quite useful for finding the point of an intersection after you've found the relevant t-value. The code for it is very simple. It is just the equation from the previous episode. We now have the intersection object. So this is used to store information about where a ray intersects an object. So we will go to some function to check whether there's any intersection, and then we'll get this out. And by dissecting this intersection, we can get all of the information we need about that. So at the moment, there's not much to put in there, but later we'll want to include things like the materials, the direction of the surface, all sorts of things. But for the moment, we don't need to worry about too much. So here we just store the ray that was doing the intersecting, the t-value, so how far along the ray the intersection was, and the shape that it intersected. We will be adding more details that it stores later, but for the moment this is all we need. So again, we have a few ways to construct them. A default, copy an existing one, but we can also make it from array. Now, notice that we don't have a constructor that can really fill in the results of the intersection. The idea here is that it's not filled in by the constructor, but instead we pass the intersection into the function, which fills it up, and then we get back the filled up one. So we don't create them with all of these details pre-filled. So these are the three constructors. So the first two really aren't that interesting, but the final one, we should pay attention to the default values here, because in the case that there is no intersection, this is what we'll actually get out. So the t is the maximum t for the ray, and the shape is null. And so by setting this t to this maximum, this is what will actually be used for the maximum checks later on. So setting t to the right value here is quite important. We then also have the deconstructor, which does nothing. We have equals, which is really just to make the code look nice. And then we have two functions here. We have the intersected and position function. So these are quite simple. The intersected function just says whether there has been an intersection, whether the ray we're talking about has actually hit something or not. And the position function gives the position of that intersection if it exists. So these are done fairly simply. So to check if we've intersected something, all we need to do is check whether the shape we've intersected exists or not. So by default it's set to null, but if we do intersect with something, then it will be updated to be whatever we've hit, and it won't be null anymore. And to find the position where we intersected, we can just use the raise calculate function with the relevant t-value. So we've sort of already built that. And we're just sort of giving it another neat name to make it a bit easier to use. So now let's talk about the shapes and how we actually fill up this intersection object. So here we have a generic shape class. So this doesn't represent any specific shape, but is more a template for what any shape must be able to do. So the key things that we want all our shapes to do is these two functions. So this is really the bulk of the ray tracing. It's where we actually trace the rays. So we have two here more for a speed thing than any difference in functionality. So intersect, this is the sort of really heavy lifting one. This goes and finds where it intersects, and it fills that intersection object with all the details it needs. Does intersect is much more lightweight. It just says, does the ray actually hit this shape or not? So sometimes with the does intersect function, we'll be able to take some shortcuts. That mean we don't need to calculate all of the details we would for the other one. So sometimes we can speed things up a little by using that one. The equals 0 here is just saying that this function doesn't actually exist here, but any subclasses will have to implement it. So the first subclass we have is a shape set. So this isn't a shape either, but it's a group of shapes. So what we're going to do is to describe a scene, we'll create a single shape set, and then we'll shove everything into it. And then we only need to really consider one shape when we're doing our ray tracing, and that's this shape set. So this makes it much easier. We don't need to keep track of lots of different objects and run the intersect functions on them all. We've just got one, and that will then do the entire scene. So this needs to store a list of shapes, and we use the vector class because it's a little bit easier to work with. It is a bit slower to add and remove objects from, but during the actual ray tracing, we're not really going to make any changes to it. And in terms of accessing the elements, it's just as quick as an ordinary list. So we can get away with this and making our lives a little bit easier. So this has a constructor, which doesn't do anything, and a destructor, which doesn't do anything either. Now, we might want to consider destroying all the shapes that are stored in the destructor, but because of the way we're going to structure the scene creation, this won't be necessary. We'll do that elsewhere. So we also want to be able to add shapes to a shape set. So we'll go look at the code for that. It's here. All it does is just pass it on to its big list of shapes. Nothing that interesting. And now we have the intersect and does intersect functions, the really important ones. And again, the shape set kind of cheats here. It just sort of loops through all the shapes it has and asks them to do their thing with it, and doesn't really do anything itself. So we need to keep track of the does intersect value here, because we need to return whether or not we've hit anything. And then we want to loop through every single shape in our list. So this is how we loop through vectors in C++. That's all we're doing here. And then all we do is we get the current shape, and we ask that shape to intersect and fill the intersection with its details. Because we're not interested in whether it's or not the rays hit the shape set. We're interested in the shape, this very specific shape within the set that it intersects. So that's why we don't then change any of the values afterwards. All we do is remember that we've hit something, and after the loop we return. Now we do need to do this for all shapes, because we're really only interested here with the intersection of the closest shape. We're not interested in the ray going through the object and the one it hits afterwards. And because we don't know what order the ray will go through these, we have to test every single one here. And this is one of the times where the does intersect function is quicker, because all we need to do is loop through the shapes, and as soon as we hit one, we can finish. Because it hits something. It doesn't matter if there's something else earlier. I mean, it still hits something. That doesn't change whether or not it hits. If we don't find anything, we do have to keep going, because there might be something else that it does hit. So we can only return false after we've been through everything. But sometimes we can return true a little bit quicker than we would be able to with the normal intersect function that gets all the details. And now we get on to the real shapes, the things that we'll actually put in our world. So the first thing here is the plane. So I described this in the previous episode, but this is like an infinitely large, flat piece of paper, extending forever. And we can describe it with just a position on the plane, so any point on the plane, and its normal, which is the direction perpendicular to the plane. And so to construct a plane, we need these two pieces of information. And we'll also have a destructor which doesn't do anything. So if we look at these, the constructor is very routine, and then the intersect function. So here we just want to compute the result of the equation that we discussed in the previous episode, but we're going to be dividing by this value here, d dot n, which is the direction of the A dot product with the normal of the plane. And now if this is 0, then we don't actually intersect at all. So we can just return false and stop there. And it's important we calculate this first and check it's non-zero, because we need to divide by it, and we can't divide by 0. It's important to keep track of that and be careful with it. But if we do find that we do intersect, we now need to calculate the t-value, which requires us calculating this other dot product here, and then we have our t. But we're not finished. We need to check that our t is within the valid range. So we check if it's less than the minimum allowed values, which is just our constant. If it is, then we're not interested in this. We don't intersect. This would mean it's behind the start of the ray, or it's the object the ray's coming out of. We also want to check that our t isn't larger than the current best of the intersection. So if it's greater than the intersection's current t-value, then either it's outside the range we're interested in, or we've already found a closer object. In either case, we're not interested, and we can consider that we don't intersect here. Now, after we've gone through all these checks, we can now fill the intersection with the details we've just calculated, so that's giving it the correct t-value and giving it the correct shape, which is just this. After that, we can return true. We have intersected. Now the does intersect function, again, calculating d.n and checking that is the first thing we do. But we can't just stop there. We need to check that it's still within the required range. So we really don't save much time in this version of the function. And now the other shape we talked about, the sphere. So this can be described by a center point and its radius. And its constructor will take those two values. Its destructor does nothing. And it has the two ray tracing functions. So if we look at the code for them, constructor's routine. Now this intersection function is a lot more hefty than either of the ones we've been through before. So the first thing we need to do is, as I explained in the previous episode, the neat little trick of only actually having to consider spheres centered on the origin. So this local ray is taking the original ray, and then we subtract the center point of the sphere from it. And this sort of moves the ray and the sphere together in a way so that they're positioned with the sphere over the origin, and it makes the rest of the maths a lot simpler to work with. So now we've got this ray, we're not actually interested in the one we were given anymore. And throughout the rest of the function, we will use this local one. And even the non-positional values, everything has been copied across by this equals sign here. So that's all fine. And then, if you remember, this ultimately comes down to solving a quadratic equation. And the way we're going to do this is calculate the quadratic coefficients. So that's the number we multiply by t squared, by t, and on its own. We call them a, b, and c. And these are calculated just as we described in the previous episode. So the first thing we need to do is check whether we intersect. So we can do this by finding what's called the discriminant of the quadratic equation. And I won't go into detail in this now, but the point of this is, if it's a negative value, then there's no solutions. If it's 0 or positive, then there are. So what matters is the case where it's negative. That way we know we don't hit, we can throw this away, no intersection. We're just sort of shooting past by the side of the sphere somewhere. Otherwise, if this is a positive or 0 value, then we do hit the sphere somewhere, so we need to find the t values. Now, we're going to consider the cases of the discriminant being 0 and not 0 together. This means that we might have t1 and t2 be the same, but it just makes it a bit neater and more consistent to write it like this. And it doesn't affect the accuracy of the final result. So this is how we calculate the two t values. And then, as before, we need to check whether they're in the required range. Now we do this a little differently because there's two possible values. So the way we do this here is first, check if t1 is in the valid range. And if it is, great, we can set the intersections t value to this. We then do the same thing with t2. And notice we use an else-if structure, because then at the end we have this else statement which represents the case that neither of them is in the valid range. And this is where we can return false. So if we get to this bit, then we haven't actually touched the intersection at all, which is exactly what we want to have happened. But otherwise, if we get down here, we know that else hasn't happened. So we know that either one of t1 or t2 is the right one. It doesn't matter which here. We just need to fill in the rest of the information, and that's just saying what this shape is. And then we can return true to indicate that we have found an intersection. Now the does intersect function, again, like with the plane, it doesn't save much time. Again, we have to calculate all the quadratic coefficients, we have to calculate the discriminant, we might get this early get out clause, but if not, we still have to calculate t1 and t2 to check they're within the required range. And this is going to be a common theme. Generally, the does intersect function for these sorts of shapes doesn't get much savings in terms of speed. But with compound shapes like the shape sets, and we will have more like these later on, that's where you get the real savings. Because you can exit early if there's an intersection, and while you can't exit the whole thing early if there isn't in those cases, you might be able to get more of the early exits in the individual does intersect functions. So there are savings to be had by splitting up the functions like that. And they will end up being reasonably significant in much busier scenes with lots more shapes and lots of various things going around. So that's it for this episode. So in the next episode we are going to discuss cameras, and then once we've done the code for cameras, we will actually be able to generate our first image. So I look forward to seeing you then. Thanks for watching, and goodbye.